leading to the decision. And that means that you will have only, I would say, two cases. So L over D, you see that in the second case, when the danger of distortion is existing, you are forced to go to a long intake. If you go to a long intake, that means that the L over D will be maybe equal to 5. This is when you need really to have a protection against distortion. But the RAM recovery will then decrease. No other solution. If the distortion danger, is not existing, if it's not existing, then you will take a very short value of L over D, and the RAM recovery will be quite high. And there is no really a reason why you would select a L over D that is 2 or 3. You will go into the direction of 0.5, maybe 1, and you will go in the direction of 5, even maybe 6, maybe even 6 here. We say very often that this parameter is between 0.5 and 5. In fact, this parameter is in the region of 0.5 or in the region of 5, not most probably in between, because there is no reason. You have a danger of distortion, then you go to 5. You don't have a danger of distortion, then you go to 0.5. And so, globally speaking, if we can say it like this will be more for civil transport aircraft that you will be here, and here you will be more in military aircraft. So fighters, combat aircraft, that will be more in this region. And in between, normally, there is no real reason to go for something that L over D, let's say, equal to 2.5 or 3. There is no real reason for that. And so you see that intakes, on the contrary of what we have mentioned before, is really, let's say, in a conflictual situation between request of a high RAM recovery and request of a very good protection against distortion, okay? Leading to a very different shape or length of the intake in both cases, okay? Also, something that is extremely important, this is, let's say, the bluntness. The bluntness, the blunt character of the lip. I have represented a lip that is very blunt here, and this very blunt character is not always possible, because if you have a military aircraft or high-speed aircraft or supersonic aircraft like the Concorde, you will be forced to take lips that are, so of course it will be a long intake, but you will take lips that are much sharper, with much less bluntness. Why? This is because if you have a shock with a blunt lip like that, it will be a very strong shock where you will have a large loss in total pressure. And with a supersonic flow or highly subsonic flow with such a blunt intake, you would have a very low RAM recovery because the shock you would have would be too strong. And that's why, in this case, in the supersonic aircraft, you will have the intake as sharper lips than with a subsonic aircraft. Why do I say that? This is because when you are in a takeoff condition, you see that it's much more difficult to follow the shape of the lips. And what will you have in this case? You will have a large flow separation on the lip that will lead to, in fact, distortion when you are taking off or when you are at low speed. Whereas in this case, it's much easier to follow the lip because you have a much smoother movement when you are doing this contour of the lip in order to go to the section A1. So you see that not only the L over D is important, but also the radius of the lip here that will be very different compared to the curvature radius that you have there. The curvature radius here and there is very different, and this is also a feature of the geometry of the intakes. And finally, there is another ratio that is important. This is the ratio between I and ATH. So you see that you are changing the section of the flow, and you have AI larger than ATH, and the ratio between these two, this is what we call the CR, the contraction ratio, the contraction ratio that is defined as a ratio of sections or ratio of diameters, but more of sections, because if you are non-symmetric, this is a ratio of sections and not a ratio of diameters that is only valid when you are symmetric. And this ratio is also something important, and it cannot become too large. It cannot become too large, because if it's too large, you will have a too large reduction, and with a too large reduction, it cannot become too large, because if it's too large, the ram recovery will decrease a lot due to the presence of the shocks here, and also because you will be forced to make a big turn in this direction, and that could maybe lead also to, that could lead also to separation of the flow at the, let's say, inner side of the diffuser, leading to some distortion that is entering into the intake. So it's a very complex problem, the geometry of a subsonic intake by the choice of the L over D, very short in civil transport aircraft, 0.5, with the ambition in cruise to have very low friction, so that in cruise you have, in this case, a ram recovery that is certainly equal to 0.99 or something like this in cruise. And at takeoff, of course, when you are in this situation, a bit lower, even in cruise it can be 0.994, 0.995, a very, very high value. And when you are at takeoff, it will be with this convergent, divergent, then maybe more value like 0.98, 0.975 or something like that. Whereas in the military systems, you can have a much lower ram recovery in cruise, maybe only 0.95, something like this, but mainly at takeoff, you can have something like 0.8, maybe even 0.75. This is quite possible, because you are, let's say, adding behind each other the very bad situations. You have a much too long intake. Having a much too long intake, you have also this feature of the curvature radius at the entrance of the intake, so near the entrance lips, that will accelerate more the flow. And so you will combine the two problems of having it's here, strong shocks and a lot of friction, because it's long at high speed, so 2 times more friction. And so there are, in fact, 3 reasons at least to have a short ram recovery at takeoff in the case of a long intake. It's long, the Mach flow rate, the Mach of this flow is higher, and you will have shock because you are in a takeoff condition. Okay? So, very complex problem. Also, with intakes, you need to discuss also other, additional points. So, what are the additional points that you should have to discuss? So, certainly, an important feature is also the mass. So, an air intake, it's very special because it's not the responsibility of the engine manufacturer. This is the responsibility of the aircraft designer, and this is an external company that is building the intake. When you take the engine out of the aircraft, the intake is staying on the aircraft. It's not a part of the intake of the engine. But we need to discuss that because it's so important on the engine performance. And so, as this is not a part of the engine, but influencing the engine performance, certainly it must be a lightweight unit. Also, the important point is the cross-section, because the air intake will add drag to the aircraft. It's increasing the cross-section of the aircraft. And you must be very careful with what is the size of the intake that is visible from the front of the aircraft. Maybe you can try to put a part of the intake buried into the aircraft so that you are not influencing the cross-section of the aircraft. Okay? Also, a very important point is that the intake must deliver the maximum mass flow rate, and also without distortion, or at least with the minimum distortion. What do I mean by that? Of course, if you have a classical aircraft with a wing that is like this, and if you put the engine here, the flow is entering into the engine very pure, not so much influenced by the presence of the engine, not so much influenced by the presence of the fuselage, not so much influenced by the presence of the wing. But if you put the intake or the engine here, for example, near the fuselage, or if you put the intake under the fuselage, so like this, like in the F-16 or in other aircraft on the side of the fuselage, on this side of the fuselage, what will happen? You have here a boundary layer